Welcome to EPG Pathshala. In this module, we shall look at subject-specific regression for generalized linear models. The essential tool which we shall use here is the mixed effects model, or also the random effects model. The random effects model is something which you have seen before, but in a different context. So in the paper on linear models, you have seen the random effects model when we are looking at, say, a number of varieties or a number of sites which have been sampled from a larger target population, and we wish to have results which not only hold for our selected sites but for the entirety of this target population. So in this case, we have a random effect, and the name random comes from the fact that we have a unit which has been randomly selected from the population. However, as we shall see in this module, the random effect comes in useful in many different contexts. So here we shall see several regression plots and see that random effects can be used in the case where we have different intercepts or different slopes for each of the subjects. Now, of course, we can address this using a fixed effects model as well, but if you have a different intercept for each of n subjects or a different slope for each of n subjects, this will greatly multiply the number of parameters, and any inference related to the parameters will be imprecise. The asymptotics will also become problematic because the number of parameters will depend on the sample size. A way to reduce this is to make an assumption about the distribution of the random effects across the population, and in this case we are able to reduce the effective number of parameters. An extension of the random effects is the mixed effects model. The mixed effects model is a very popular tool in the statistical literature. In its simplest form, it can be used for the kind of experimental design situations which you have seen in some of the previous papers. It can also be used for many other relatively more complicated situations. It can be used to model longitudinal data, missing data, nonlinear relationships, and we shall get a glimpse of some of this in this paper. Finally, we shall look briefly at the principles of estimation. So while we use least squares for the case when we have fixed effects model, in the case of random effects model, note that it is not possible to estimate a quantity which itself is random, and hence rather than a best kind of estimation, we use the principle of best prediction. So although we will not go into details, we will briefly touch upon the concept of best prediction for a GLM. Finally, we shall also see something which is a difference between the case where we have a continuous outcome and the case where we have a GLM. You know that a random effect is parametrized as a deviation. So the random effect for the ith experimental unit denotes how much it deviates from the overall average. If you add this random effect back to the overall average, then we get a measure which can be interpreted as the contribution of the ith subject. Now, because of the nonlinearity which arises in GLMs, we shall see that this kind of an assumption does not hold for the case when we have GLMs. This is one difference between a linear model and a GLM. Learning objectives for this module. We shall first define the random and the mixed effects model. Next, we shall introduce the concept of subject-specific longitudinal data and see how the random and mixed effects model can be used to make inferences in this case. Next, we shall generalize these concepts to the case where we have a generalized outcome, that is, an outcome from the one parameter exponential family. And finally, we shall touch upon some of the properties of subject-specific generalized linear models. Subject-specific models for longitudinal data. Let us first review the concept of fixed and random effects. You have seen fixed and random effects before in the papers on experimental design and the preliminary papers on regression. So fixed effects are parameters which are associated with some well-defined entire population. Now, random effects are also parameters in some sense, but they are parameters associated with individual experimental units which are drawn at random from some larger population. A model which contains both fixed effects and random effects is called a mixed effects model. Now, you have seen the use of fixed effects, random effects, and mixed effects in the concept of experimental design. In this paper, we shall see how these similar concepts are used in the context of longitudinal analysis, more broadly, in the context of a wide variety of models where the outcome can be a member of the exponential family, that is, we have a generalized linear model. The mixed effects model can be used to model longitudinal data, but it can also be used to model an additional number of complications which can arise for observational data. And hence, this general form of the mixed model is quite useful in statistical applications. So let us start with a motivating example, which is from the NLME library. So here we have a number of rails which we have categorized as 1, 2, 3, 4, 5, 6. And on the x-axis, we are looking at the time taken in nanoseconds for a particle to travel across the rail. So you can see that the particles tend to be clustered to different extents on each rail, and that it appears that the time taken to travel across the rail is quite different for each rail. We would say then that there is a subject-specific, in this case, a rail-specific effect. So to begin to model this data, let us begin with the simplest situation where we completely ignore the subject-specific effect and fit the model Yij equal to beta plus epsilon ij. So I is equal to 1 to n, the number of rails, and j is equal to 1 to ni, which is the number of observations for each rail. Beta is the overall mean as well as the mean for each rail, the mean time taken to travel across each rail. And as I said before, we have ignored the fact that this time could vary with the rail. Epsilon ij is a noise term, and we assume for the purpose of inference that epsilon ij's are IID normal 0 and variance sigma squared. So here we have fitted this model and found the residuals, and the figure given on this slide denotes a box plot of the residuals. Now, as you can see that there appears to be some kind of systematic trend in the residuals, which is always alarming. So the residuals are clustered at different points, and also it appears that the variability of the residuals for each rail are quite different. So let us make an improved guess at model fitting and include the effect of the rail. So here, rather than fitting the model Yij equal to beta plus epsilon ij, which ignores the effect of rail, we have fitted a model which is Yij equal to beta I plus epsilon ij, I equal to 1 to m, and j equal to 1 to ni. So beta 1, beta 2 to beta m are the mean times taken to travel across the ith rail and their m fixed parameters in this model. So we fit this model using usual linear model theory, that is least squares, and find the residuals and do a box plot of the residuals as before. Now, as you can see, there is no systematic trend in the residuals, which is reassuring, but the variability of the residuals still continues to be a matter of concern. In fact, if you find the confidence intervals for the parameters beta I, you will see that they are rather large, and this stems from the fact that we have introduced additional regression parameters, one for each rail. So the excessive number of parameters means that our inference will tend to be somewhat imprecise, and this is reflected in wide confidence intervals for the beta I. If you wish to analyze this data set, you can look at the NLME library. We next introduce the random effects model in this context. We shall change the model before to Yij equal to beta plus Bi plus epsilon j. Now, of course, it is possible to write beta I as beta plus Bi. However, a difference with the previous fixed effects model is that while beta continues to be a fixed parameter, our Bi's are now random. That is, we are assuming that Bi, which represents the deviation from the overall mean beta for the ith rail, itself has a distribution across the rails, and this distribution is normal and given by Bi follows normal 0 sigma b square, and this is independent of the epsilon ij's which follow IID normal 0 sigma square. This model has been referred to in the literature variously as a hierarchical model by Lindley and Smith or a multi-level model by Goldstein. So we have random effects here, and as I said in my introduction, the term random effect stems from the fact that we have parameters, but these parameters are random because they correspond to units which have been chosen at random from a larger target population about which we would like to make inferences. The way the random effects have been parametrized, so instead of beta I, we are writing it as beta plus Bi, which means that beta can be interpreted as the overall mean and Bi is the deviation from the overall mean for the ith rail. It is quite common to parameterize a random effect as a deviation from the mean, and that is why we assume that the deviations are normally distributed and that the mean of these random effects can be assumed to be 0. Now note that the effect of this assumption is that the covariance between observations on the same rail, so say the first and the second observation, is given by yi covariance between yi1 and yi2, and because yi1 and yi2 shared the same common random effect Bi, it turns out that this covariance is given by sigma b square divided by sigma b square plus sigma square, where sigma square is the variance of the error term. Thus, introduction of the random effect has induced covariance between observations on the same rail. Now, there are several extensions of this model and they can accommodate complications of various degrees. So the random or the mixed effects model, where one subset of the parameters are fixed parameters and one subset are random, can be used to handle a large variety of complications. So one of these, for example, is longitudinal data analysis. It can be used to handle smoothing. It can be used to model missing data, hierarchical data, latent variable models where some of the variables we are interested in are essentially unobservable. And more interestingly, it can also be used in situations which address a combination of the features listed above. This is why the mixed effects model is a very common tool in the statistical literature. In this module, we shall concentrate on its use in the context of longitudinal data. So here is a very common example motivated by the use of growth curves. This is taken from the orthodont dataset, which is included in the NLME library in R and is a very well studied dataset with vignettes which are available from the CRAN website. So here what we have done is we have looked at the growth of girls versus boys. So more specifically, by growth we mean the distance from the pituitary to the pterygomaxillary fissure, and we have plotted this against age for a sample of 16 boys and 11 girls. So this plot is given on the left panel of the slide. On the x-axis we have age, while on the y-axis we have measurements on the distance from the pituitary, the pterygomaxillary fissure, measured in millimeters. Now you can see that each of these scatter plots looks rather different, and it suggests that there is a strong subject-specific effect. A very simple way, though perhaps not a statistically ideal way to model this, would be to fit separate linear models to each of the subjects. We have done this, and here we list the intercepts and the slope coefficients for the sample of girls in the sample, and we see that there is quite a variation in the intercept as well as in the slope. It is also interesting to look at the correlation between the intercept and the slope and to try to identify if there is one. Now note that the slope coefficient has been applied to the centered variable, which is age minus mean age, which is 11. And in a subsequent slide, I'm going to make some observations about the effect of centering. However, our takeaway message from the previous slide is that there is strong subject-specific variation, and the tool which can be used to model this is the mixed effects model. So this slide presents the general mixed effects model for longitudinal data. For the previous example, it would be given by yi, which is the vector of observations on the ith subject, equal to xi beta plus zi bi plus epsilon I. So yi is the entire vector of the growth measurements taken on the ith boy or the ith girl repeatedly across the 11 ages. We make the assumption that beta refers to fixed parameters and the bi's are random effects, which are assumed to have a multivariate normal distribution with mean vector 0. The bi's are multivariate normal random effects which have the mean vector 0 and the dispersion matrix psi. The elements of psi may be assumed to be known or they may be unknown and estimated from the data. Epsilon I are the errors, and these are, as is standard, assumed to be normally distributed with mean 0 and sigma square I. The bi's and epsilon i's are independent. x1 to x11 are the design matrices corresponding to the fixed effects, and z1 to z11 are the design matrices corresponding to the random effects. If we fit a model which only has a random intercept, for example, then z1 to z11 are all given by this column of 1s. Parameter estimation can be done by a maximum likelihood and or by a related technique called restricted maximum likelihood. In fact, it is common to estimate the fixed effects parameters beta by maximum likelihood and all parameters related to the variances by restricted maximum likelihood. To know more about this, you are referred to the modules on longitudinal data analysis. This is a quick glimpse into the fact that the mixed effects model can quickly be scaled up to handle a number of complications. So the data given on this slide refers to another very popular public domain longitudinal data set available from R, which relates to the size of trees. So we have some trees which were exposed to ozone and some trees which were not, and we measure the size of the trees. So the regression model given on this slide relates the log size of the ith tree on the jth day. The regression model given on this slide relates the size of the ith tree on the jth day to whether or not the ith tree was exposed to ozone, as well as to a function of day. Now, if you make a scatter plot for this data, you will see that it does not quite support the hypothesis that log size increases linearly with day, and a way to get around this is to assume that it is a nonlinear function of day. Now, you can of course specify the kind of nonlinearity, that is quadratic or cubic or exponential, but another way which is popular in the statistical literature is just to say that it is a function of day, where we specify nothing about the function f except that it is smooth and wish to estimate it from the data. It is possible to show that there is a certain mixed model representation which can be used to recover the additional function f of t. Now, because the mixed model can also be used to handle the random intercept, it turns out to be a very easy way to seamlessly model the effect of a random intercept as well as nonlinearity in response to day, and hence is a very useful tool. So in the two panels given here, we look at the coefficient of ozone, and in the right panel, we are looking at the estimated function f of t, which, as I said before, was estimated using a mixed model representation. For more reference to this, you are referred to the book by Rupert and Wand. The generalized linear mixed effects model. The mixed effects model given on the previous slide can be generalized in the following way by introducing a link function H inverse. So here, instead of saying expectation of yi given bi xi zi is equal to xi beta plus zi bi, we introduce a link function and relate H inverse of expectation yi given bi xi zi equal to xi beta plus zi b. Now this is done from the same motivation as is done generally for a GLM, that is to preserve the effect of the interval. So for example, H could be the logit function, and in that case we would say that logit of pi I over 1 minus pi I equal to xi beta plus zi bi. We assume in general that yi arises from the one parameter exponential family, that is f of yij given bi xij zij is equal to exponential phi inverse yij theta ij minus psi of theta ij plus c yij phi. So this is the representation of the one parameter exponential family, where theta ij denotes the canonical parameter and phi is an optional scale parameter. Now, of course, eta ij is the linear predictor. It is given by eta ij equal to xij prime beta plus zij prime bi, and we assume that eta I summarizes the effect of all covariates on yi through the link function H inverse. So here are some common generalized linear mixed effects models. The first is logit of mu ij equal to log mu ij over 1 minus mu ij equal to eta ij, which is the logit model. We can also have the probit model, which is phi inverse mu ij equal to eta ij. Our assumption here is that yij given mu ij follows the Bernoulli distribution with mean mu ij. We can have the corresponding model for counts. So here log of mu ij is equal to eta ij, where yij given mu ij is assumed to follow Poisson with mean mu ij. Now eta ij in either case is given by xij prime beta plus zij prime bi. We can also generalize this further to introduce the concept of categorical data. So instead of a binary outcome, we have a categorical outcome, and we can model this by assuming, for example, the logistic model. So logit of gamma ij s is equal to eta ij minus kappa s plus 1, or the corresponding probit model, phi inverse gamma ij s equal to eta ij minus kappa s plus 1, where pi ij s is the probability of yij being in the sth category given eta ij, equal to pi ij s minus 1 minus gamma ij s. We assume here that yij given eta ij follows a multinomial distribution with parameter 1 pi ij naught to pi ij s minus 1. There are several representations used for the mixed effects model. One way to represent the mixed effects model is as a nonlinear model with an error term. So for example, yij is equal to pi ij plus epsilon ij zij1, where pi ij is h eta ij, h being the link function, and zij1 is equal to square root over pi ij into 1 minus pi ij. The reason that this is done is for the convenience of fitting. Another formulation which can be used to motivate this model is a latent variable formulation. So for example, the plot here refers to a situation where we have a categorical outcome and there is a corresponding unobserved, that is latent variable, and depending on the category into which this latent variable falls, we observe the particular value of y. So a particular range of this unobserved variable, which is denoted by the shades of gray in this slide, corresponds to particular values of the outcome variable. We shall see more on this in the modules on polytomous regression. Another comment is related to endogeneity and centering. Now, omitted subject level covariates may be confounded with time-varying variable. For example, assume that we have a linear random intercept model where there is only a single time-varying covariate Z and a single unobserved subject-specific covariate W. Now, W and Z correlated means that Z is confounded and hence we have omitted variable bias. Z is endogenous or correlated with the random intercept, which represents all unobserved subject level covariates. Now, a way to get around this is to observe that W cannot be correlated with Z if we force the mean of Z over time for subject I to be the same for all subjects. This can be achieved by subject level centering. That is, instead of using the covariate Zij, we use Zij minus Zi bar, and this ensures that there is no confounding. This is essentially what was done for the orthodont dataset. One interesting difference which arises in going from linear models to GLM is the interpretation of the model parameters. Now note that if y is continuous, Yij equal to beta plus bi plus epsilon ij, and because of the assumptions about beta, if we take expectation over bi, it follows that this expectation is given by beta. So expectation of beta plus bi is equal to beta, which means that while bi can be represented as a deviation, beta plus bi, expectation of beta plus bi is equal to beta. So beta can be interpreted as an overall mean. On the other hand, assume that we are using a link H. In this case, the overall mean is obtained by integrating out the random effect, and expectation of Yij given Xij Zij is equal to integral of h Xij prime beta plus Zij prime bi multiplied by phi of bi 0g into dbi, and we cannot guarantee that this will be equal to h of Xij prime beta. In fact, it will not be equal to h of Xij prime beta based on what we know on the expectation of nonlinear functions. Thus, the parameter beta here does not have the clear interpretation of an overall averaged mean. That is, if h of Xij prime beta plus Zij prime bi is, say, the log odds for the ith subject, we cannot say that h of Xij prime beta is the average log odds across all subjects. I would recommend that you perform the necessary calculations and satisfy yourself on this regard. One last slide which briefly touches on estimation and inference. We shall do more of this in the modules on longitudinal data analysis. Now again, because of the complications introduced by nonlinearity, estimation here is slightly more different. You are recommended to read the paper by Breslow et al. To get more perspective on this. So Breslow describes two techniques of estimation. One is marginal likelihood, where we integrate out over the random effect, and another is penalized quasi-likelihood, which arises from an expansion of this integral using something called Laplace's approximation and leads to the technique called penalized quasi-likelihood. So I have mentioned the concept of REML to estimate variance parameters. Here also it is possible to arrive at a REML type criterion to estimate the variance predictors. We are interested in getting some kind of prediction of the random effects, and this can be done using the concept of best prediction, though its implementation here is of course more difficult, and it is possible to improve upon the set of estimates arrived using these procedures using further bias correction applied to the PQL estimator. In this module, we have looked at the use of subject-specific generalized linear models. Now, although the basis for this is the simple random effects model which you have defined in experimental design, this model can be quickly scaled up to handle a large variety of complications, and this is why it tends to be very popular. Generally, we have focused on longitudinal data, but have also seen that this model can be used to handle many complications like latent variables, missing data, nonlinear dose-response relationships, and so on. For longitudinal data, we introduced the orthodont data set and saw a scatter plot from this data set. This seems to suggest that there is a lot of subject-specific variation in growth over ages, and to model this, saying, for example, that we wish to have a subject-specific intercept, it is possible to extend the concept of the mixed model. We have seen extensions of this for the case where the yi is no longer continuous but arises from the one parameter exponential family. So we have defined the generalized linear mixed model for the case where we have a logit link, a probit link. We have also defined it for the case of count data using a log link, and seen that it is further possible to use this same model for the case where the outcome is not binary but can be categorical. This model can be framed in various ways. For example, it can be framed as a nonlinear model, or it can also be motivated from the context of a latent variable formulation. One difference which distinguishes the GLM from the linear model is that the random effect is one difference which arises when we make the